So this is my email, if you understand. So my name is Talia, for those who don't know me. I'm going to be the TA. If you have like problems, questions, whatever, this is my email. My office is like basically here, but sometimes I sit in Resnick, so you can just check on me. And yeah, that's basically it. So I guess it already told you, but just in case, the course is made from, like the grade of the course is made of 80% going to be the exam in the end of the semester. You're going to have 10% from the homework, and then 10% from like a mid-semester test.
There will be also a second test?
Yeah.
Okay.
So you're going to have the same as you have like regular exams. So you're going to have. So it's only started like last year. So I don't know if it's going to be exactly the same, but it's usually the one case we saw. It's stuff that are more based on like the lecture and not necessarily like the kind of like regular questions that you will see in the test. It's mostly something that you don't want to do to make sure that people come to the lectures. So come to the lectures. Okay, I think that's it. Anyone have questions about the course before we start to talk about physics? No? Okay. So,
when approximately will be the mid-semester test?
Around the mid-semester.
Yeah.
I don't know.
In weeks.
He said 2 weeks before the end of the semester. If you would listen, you would know.
So I guess that I don't know. Like we didn't talk about specific time. Okay. So what we're going to talk about today is the Obix equation, which we started to talk with video about. Like I hope more than started. So to talk about the Obix equation, we first need to talk about Hamilton's equations. So in general, in physics, we have Hamiltonians, that you know from previous courses. And this Hamiltonian would be is a function of the coordinates of the system. So if you work in one-dimensional, one-particle system, you're going to have the coordinate x and the momentum of the particle, which will be t. If we have more particles, each one of those particles is going to have position and momentum. If you work in higher dimension, which is what we're going to do, for example, 3 dimension, we're going to have position and momentum for each dimension, which means overall, if we have n particles, we're going to have 3 n's degrees of freedom.
6
n's degrees of freedom. So we have Q1, Q2, P1, P2, etc. So the way those coordinates evolve in time can be described by the Hamilton equation. So for each coordinate, for each like set of coordinates, so Qi and Pi, the derivative by time of Qi is equal to the derivative of the Hamiltonian by the momentum with the same index, so the same dimension and the same particle, and the derivative of the momentum by time is the same but with minus. So it's the derivative of the Hamiltonian with the position qi with minus. So those basically are the equations. So okay, so let's look at like tiny example, and then we're going to see we're going to continue to talk about qubits. So let's take like the simplest possible scenario that exists. So one-dimensional full particle. So a single particle in a single dimension. So the coordinates are only going to be x and px. So the Hamiltonian is only going to be made from the momentum because we don't have any potential. So this is going to be p squared over 2m. And what we want to do is to use those equations to find x and p as function of time. So the first equation is going to be for x. So the derivative of x with t is equal to the derivative of h with p, which is p over m. So this is equation of motion that you. This will give equation of motion that you can recognize from like first year, I guess. And the derivative of the momentum with time is equal to minus the derivative of the Hamiltonian with x, which gives 0 because the Hamiltonian does not depend on x. And then this gives us, so the momentum as function of time is a constant. We call it p0 because why not? And therefore, the derivative of x with t is equal to p0 over m, and then is x as function of time will be p0 over m multiplied by t plus some constant that we call it x0. So this will be the solution for any time, and with the appropriate initial condition we can also find p0 and x0. So easy. So if we have very little particles or very low dimension, these equations were maybe like easier or harder to solve, depends on the system. But because we work now in statistical physics, we're going to talk about like very large number of particles, like a Avogadro number of particles. So we're going to have far too many equations to solve. All of those equations are going to be coupled because the Hamiltonian will depend on all of the different coordinates. So this is clearly not a very convenient way to work. So what we're going to do? If someone wants to open it, do you want to open the window?
הידית למעלה.
תסגור. לא, למה לא? הפוך.
טוב, אני לא יודע, אני נעשה
Okay, so now instead of talking about each specific coordinate, we're going to define a density function, which name rho. And this function, as you can understand from its name, it gives you the probability of the system to be in any value of q and p for any given time. So you have the phase space that's defined by Q and P. So if you have like one-dimensional particle, like a single one-dimensional particle, you're only going to have the phase space going to have only 2 dimensions. So I can like actually plot it on the board. For higher dimension, we're going to have, as we said, 6 and degrees of freedom. So this is going to be a bit more complicated to actually plot. But for this specific case, what we did with the Hamiltonian formalism, we said, okay, let's look at some initial point in the phase space that is Q0 and P0, which is the initial condition of the system. And the Hamiltonian is going to tell us how this point evolves with time. So if this is for t equals 0, I can use this equation to predict the trajectory of this point with time. So this is for like some point t equal t1. So now instead of looking at a single point, I'm going to have to go a little bit bigger. So instead of looking at a single point, I'm going to look at like a cloud of points around this point. And for each one of the points inside that volume, here it's not volume because it's 2 dimension, but we're still going to use the term volume. So inside this volume, each one of those points will follow basically the Hamiltonian formalism, and it's going to have its unique trajectory until at some time t equal t1, this is going to be this is going to give me some volume in other part of the phase space. So so the density function is what's described this variable of the system. It's going to describe the initial condition. So I have rho of Q0 and P0 at time t equals 0, and by use the evolutionary time of the density function, which we're going to see in a minute how can we do that, I will find rho of Qt and Pt at time t. So that's going to give me, instead of like a single value, so in that case, it's going to give me like a distribution as function of the coordinates. So what Liouville's theorem claims is that if I start with initial condition with some volume, we call that like A0, which is everything that's inside that circle. And all of those points are in time, and I plot all of those points in some time that is larger than 0. So this is let's call it A1. So A0 always have to be equal to A1, which means the volume in the phase space have to conserve with time. Conserve with time. So we have conservation of the So to get the equation, you have 2 ways to look at it. You actually have more, but you have basically 2 ways to look at that. So one way, which is what you did with Vidal, is to say, okay, this is a density function, so it has to follow the continuity equation. So it's behave like a fluid, and then you claim that this conservation of volume is what's called incompressible process, which means if I look at like a current of a liquid, and this goes through some okay, imagine this is a two-dimensional plate. So I have like a three-dimensional liquid, and it goes through the two-dimensional plate. If I take the bottle with the water, and I look at the water that goes through the bottle, all of the water that's going to come from this direction are going to come out of this direction. So I don't have flux. So that means that the overall volume of the water in that part of the space is going to be equal to the volume of the water in that part of the space. Okay, so what does it actually mean? So let's look at the full derivative of complete derivative of rho with time. I still didn't say anything specific about this function. I still don't know anything about this function. I just defined that this function exists. So if I look at the full differential of rho with time, so there are two things that can change the density function. So the first one is the actual change of rho with time, which is a partial derivative. So if rho is eventually a function, so it's going to depend on time. And the other thing is that rho also depends on Q and P. So any change in Q and P will eventually cause, and Q and P also depend on time, so any change in Q and T is going to change rho as a function of time. So I have a sum of all of the degrees of freedom I have in the system. So this goes from 1 to 6n to, so it's 3n. And then I have the derivative of rho with qi, and then derivative of qi with t. And derivative of rho with pi, and pi with t. So this is the only time in the course that we're going to acknowledge the difference between partial derivative and full derivative. So the partial derivative means that rho can depend on time. So I have rho as a function, so it depends on q and p and t. It's just a function. But overall, rho doesn't change with time, because what Liouville's theorem tells us, and we're going to prove it in like 15 minutes, is that the density function itself doesn't change as a function of time. So it's a constant through the whole trajectory, because the overall amount of water in the system doesn't change when it flows through time. So overall, all of that is equal to 0. So rho dt plus rho dqi So this is basically one form of Liouville's equation. So it means it's basically a complicated differential equation. It doesn't tell us much, but to be able to actually do something with that, we're going to use something that we already saw a few minutes ago, which is Hamilton's equation, which gives us, if you remember, it's going to give us the derivative of q and p with time. So yeah.
You said you want to be 0 because rho is just conserved.
Yes.
It's not a point.
It's conserved as function of time.
Okay.
Yeah.
Can you please speak a little louder?
Yeah, I'll try. It's hard competition, really. Yeah, so I'll finish that and then ask again if you have questions because I want to. So just a reminder, we said the derivative of q with time is equal to dh dp, and the derivative of p with time is minus dh dq. So we can rewrite that as d rho dt plus d rho dq, and then h dp minus d rho dp dh dq. So this is not a very pleasant equation, but in that case, as you're going to see in your homework, if I have a given Hamiltonian and I don't have too many degrees of freedom, I can solve this equation and get an explicit version of the function. So this is basically the equation. So one thing, that summation of all the derivatives, it's also known as the Poisson brackets, and we can write that like that. So I have h and rho. So Poisson was too tired of writing that every time, so this is just an alternative way if someone is feeling incredibly lazy. Okay, so this is the equation. So next thing we're going to do, so far this is something that you saw in the lecture. So what we're going to do next is to prove the assumption behind this equation. But before that, does anyone have a question? No? Okay, cool. Okay, so when we talk about conservation of volume, what we actually mean is that we have some infinitesimal part of volume. So this is some dV that is multiplication of all of the infinitesimal parts of all of the variables that we have in the system. So for any I from 1 until 3n, this is dqi, dpi. So this is part of the volume, and the conservation of volume happens with time. So what we do, we move from q and p to, let's call it q tilde and p tilde, which is just the same variable in different parts of time. So the claim is that this, you can define it with an integral if you want to look at like integration of, like if you want to look at like infinitesimal parts of the volume, or if you want to look at like it's depending on how you want to define the volume, but it doesn't matter. So we want to prove that this is equal to this. So if we do look at like an actual volume, so we integrate over all of the different variables. So how we're going to change from one set of coordinates to another set of coordinates, just in general.
Multiply by Jacobian.
Exactly. So if I want to write the integral of all of the dqi, dpi, etc. as function of the new coordinates, this is going to be Jacobian. It's function of q tilde, p tilde. And this is true in general. So if you want to move from here to here, what you want to do is to prove that the Jacobian is equal to 1. So before we do that, and I apologize ahead, so in a more general way, the time evolution in Hamilton's equation, you can define what's called canonical transformation. That we're going to talk about it now, and then we're going to show how this is true for any type of canonical transformation, and not just for the one that we saw for Hamilton's equation. So, okay, so I put on the Moodle like a detailed tutorial notes, and I wrote there a bit more about the canonical transformation. I don't want to talk a lot about the canonical transformation because it's not a very important concept as it is. I just need to define that in order to prove what we need to prove. So I'm going to define it, and I'm going to show you what it means, and then we're going to go back to the proof. And if someone is particularly curious about it, you can go ahead and read it out. So, canonical transformation, basically what it means is that I have initial set of coordinates like we had here. So this is Q and P. So this is like each one of them is you have like Q1, 2, 3, and etc. And I move into a new set of coordinates, which is we're going to stick to the notation. So this will be Q tilde and P tilde. And a canonical transformation means that I can write Q as a derivative of a function that I call it f2. If you want to know why I call it f2, you can go ahead and read, but for now it's just a function. So df2, the derivative of f2 with p, and p is the derivative with q. What? So this looks a little bit like Hamilton's equation, but it's not, because I don't have derivative with time and I don't have the minus. So this is just a transformation from one set of coordinates to the other. So I'm sorry, this is how it should be. And no, I find it. Yeah, okay. So this is the old coordinates and the new coordinates. So the statement is any. This is the definition of a canonical transformation, and the statement is any canonical transformation follows Hamilton's equation, and therefore also Liouville's theory. So this is everything we need to know.
It's also true for the other side. If it follows the Hamilton equation, it's
not exactly, because what you say here is that you start with a set of coordinates that follow Hamilton's equation, you go to another set of coordinates that follow Hamilton's equations. So if you go the other way around, I'm not sure.
I mean, if it follows the Hamilton equation, is it also canonical transformation?
Yeah, but if when you say that they have a set of coordinates that follows Hamilton's equation, this is one set of coordinates. So I need this is about transform from one set of coordinates to another set of coordinates. So it's not, you cannot go.
Okay, assume here that Q tilde and P tilde are the transformation is canonical also here, or here we will need to prove it?
No, so now I'm going to assume that all of those are that. Okay, so this is like a specific case of canonical transformation, and this is like a general case of canonical transformation. What actually happens that in the case of the time evolution here, the function, if we have generating function, it's going to be the action. So we have the integral of the Lagrangian and all of that. So
it will be actually Hamilton-Jacobi equation.
Yeah, so this is a bit more clear form. But it can be for any kind of transformation. I put example in the notes about transformation from Cartesian coordinates to polar coordinates. So you have x and y, and you move to like r and theta, and you see that like you can define just some function f2 that follow that follow those equations, and that is also kind of intuitive, because we know that if we change from Cartesian coordinates to polar coordinates, the physics doesn't change. It's just the variables that you use. So this is a bit maybe more intuitive. So this is canonical transformation. So it gives us a connection between the coordinates. Okay, so let's go back to the Jacobian. So what is the Jacobian? So the Jacobian of Q tilde P tilde is basically a matrix, right? So I have the derivative of Q tilde 1 with Q1 and Q tilde 2 with Q1, and in the end I have dt tilde 3n dt 3n. So I basically have all of the possible permutations of the derivatives. And we can also write that as the derivative of q vector and p vector with q, Q tilde so this is just another way to write that. So we can also rewrite that one, which is basically like rewriting the if we have a derivative of a set of coordinates by other set of coordinates, we can do like a derivative without. So this is going to be like, for example, not for example, this is going to be so Q tilde. Okay, I'm going to do without the vector, but this is the vector. So Q tilde and P tilde, Q and P tilde, and then Q and P tilde by Q and P. So I just add extra step. Okay, so this is so the first time is just the derivative of Q tilde over Q, where I keep P constant. And I can write, instead of multiply it, I can like divide like the opposite. So this will be like over dP tilde with Q constant. And now what we can do is we can rewrite the derivatives by Q and P tilde using the definition of the transformation.
What did you
I just like I divided by the opposite of that, like just do. So I have dq tilde dq and dp tilde dp, where I keep like p here constant and q constant, and then I divided by dp tilde. Just took the one over. Like I did that.
Yeah, okay.
Okay.
But here it's not a matrix. Here it's a matrix.
Yeah, this is still vector.
Okay.
This is okay. The basically what you can do is you can do it for each one of the like components. So this will not be the most rigorous proof if ever. But that stage you can just do it for each one of the components of the vector. But we keep P and Q as vectors instead of doing it every single time. So. So we have Q tilde and Q, and we have P tilde and P. So the derivative with Q, we're going to use the transformation. The derivative of Q of Q tilde, I'm going to put instead of Q tilde the derivative of F2 with P tilde. This is F2. Okay? And instead of P, I'm going to use the transformation with the derivative of f2 over q. So this is the tilde of the f2 dq. And because those are partial derivatives, I can always replace between the order of the derivative. So this is just like writing dq dp. Okay. And this is equal to that, so this is equal to 1. Actually, it's equal to the matrix, but so we prove the Jacobian for any coordinates that follow that kind of transformation is eventually equal to 1. So if we move from one set of coordinates to another set of coordinates, this is not going to change the volume through the trajectory. Questions? Yeah.
Earlier you gave an example, the transformation from Cartesian to polar coordinates.
Yeah.
But that can't be canonical since we know that the Jacobian is not 1 in this case.
From Cartesian to
Polar.
one.
It is
Does
one
not-
because you are taking the determinant. The
You,
Jacobian is not the identity matrix in the form of
That's
the
what I
matrix.
said.
But here J stands for determinant. The
No,
determinant
You take
J-
U
the
and
matrix
P.
itself.
you take Q and P.
Yes.
You also take the momentum. When you consider both of them together,
You said
You have overall-
in the face.
yes, in phase space, only in phase space. If it were just Q, that would. So that was for Liouville's theorem. If anyone is a bit lost, the important thing is to actually know Liouville's equation itself and to understand how to use it. But this is basically a differential equation. You know how to solve differential equations. So yeah. Okay, so the next short part of the tutorial will be basically about combinatorics. So you talked with Ido about ensembles a little bit, and about Boltzmann's entropy. Like, I guess you saw it in some points through the lecture. So this famous equation, if you work in the macrocanonical ensemble, this gives you the entropy of the system, where omega is the number of states for specific energy. So this I think you already know from the previous StatMech courses. So this is number of states for some specific energy. So what we're going to do, we're just going to solve two examples where we're actually going to calculate this number of states to balance out the first part of the tutorial. So the first example, is a harmonic oscillator, or n harmonic oscillator. So we work in one-dimensional. We have n particles. Each one of them is an harmonic oscillator, and we want to calculate the entropy of the system. So for one particle, we know that, sorry, this is, okay, no, I don't want to write it because we are in StatMech, but this is basically like quantum harmonic oscillators. So for one particle, we know that the energy of an harmonic oscillator is h bar omega n plus half. Now, if we have n particles, and each of them have a different quantum number, so a different value of n, the total energy, we have, so we have first a summation of all of the quantum numbers. So I have ni, where I go from 1 to capital N. And I also have, for the half, just n over 2. So each particle contributes half. So let's define a parameter m. I don't know if you see from there. So a parameter m that is just the sum of all of the ni. So what we want to ask is that for specific value of that energy, how many states can we have? So the parameter that determine what's going to be the energy is obviously m, because this is a constant. So how many options we have to distribute the different quantum numbers of the system for specific value of m. So for example, if we have n equal 3 and m equal 2, so okay, let's do that 2 because I'm lazy. So we have n1 and n2. So the different options will be 1, 1, 2, 0, and 0, 2. Right? You saw that in quantum mechanics when we talk about generality. So I have overall omega is equals 3. So now I want to do that for general value of m. So what we're going to do is to use combinatorics tricks that you probably saw in like statistics course or something at some point. So let's say we have n boxes. So each box represents a particle, and we have n boxes, and we have m balls. And we want to ask how many options we have to put m balls inside n boxes. So that will give us the way to distribute those m energy inside the different particles. So so this is also, instead of n boxes, I can use n minus 1 like blocks. Is blocks the right word?
Separator.
Like walls.
Barriers.
Yeah, so instead of n boxes, I have n minus 1 walls that separate between, it's basically what separates between the different boxes. And I have m balls, and I can put the m box inside the the m rows. So I have like 2, 1, 3, whatever. So how many options I have to put m balls between n minus 1 blocks? So overall, I have the overall number of objects that I have will be m plus n minus 1. And so basically, the number of options to organize this number of objects will be m plus n minus 1 factorial, right? Because I have that, and then I have minus 1, and I multiply all of the options. But because all of the particles are identical, in that case, they're always identical in that course. So we don't have any difference between one wall to another. Like, it doesn't matter if I put that or if I replace those two walls. So I need to divide between with m n minus 1 factorial, and the same goes for the walls. I don't have difference between one energy quanta to the other. So I'm going to divide with m factorial. So overall, this is the number of states that I have in the system. So if I want to use that to calculate the entropy, so this will be kV, and then ln of minus 1 factorial, minus ln of n minus 1 factorial minus ln of m factorial. And you can like simplify it further, depends on how much time you have. So this is one example. The second example is the other very simple system that we think of, which is a two-level system. So we have, let's do two. So we have n particles again. And each particle can have energy, can be in a state of energy which is either plus epsilon or minus epsilon. So we define, in order to solve the problem, n plus as a number of particles with energy plus epsilon, plus minus, and minus the same with minus epsilon. And now we want to calculate the overall number of states, the same as we did here. So the overall energy will be epsilon multiplied by the number of particles with plus epsilon minus the number of particles with energy minus epsilon. And we can also define this as some parameter m, or we can stay with n minus and n plus. It doesn't really matter. Depends on, you know, what what the question asked, but in that case I'm going to stay with that just because it's more convenient. So this time we won't do something too fancy, just the number of options that we have to organize the system with specific combinations of n plus and n minus is basically out of all of the n particles, how many options I have to choose n plus. You know this choose binomial coefficient. So this will be n factorial, n plus factorial, and minus factorial. So this is just definition. And again, if you want to calculate the entropy, you can take logarithm of this thing and you get the entropy of the system. So that's overall. So for the homework, you're going to have like a numerical problem with so you have some cube in high dimension, and you need to see like how the number of combinations with the entropy, and anyway, it's fun. So okay, so this is for entropy, and this is it. So I would just say, because sometimes after the beginning of the course, students start to tweet a bit. So the good and the bad thing about this course is that it starts a bit tough and it gets easier. So further you go in the course, the easier like the subjects are. So the first part is a bit more abstract, I think. And then in the second part, we study a bit more like stuff that are a bit more So just take that into account. Okay, questions?
Thank you.
מעולה. לא, יש לי אחד פיל, היום מזה פיל 4. אני יודע. מייל התחלה. אם לא ביטלנו? כבר אי אפשר לפתח. אבל הם לא מבינים לך לכל. כביכול אתה אמור לשלם את זה 300 שקל. תחשוב שאתה באמת רוצה לחלק